Cool. So today we are fortunate to have Aviral Goel from Northeastern University, and he's a student there with Yambitech. And he's going to tell us about laziness in R.
Hi everyone, thank you Matt PL for hosting me. I'm going to talk about the design, implementation and use of laziness in R. This work was published in OOPSLA last year. R has become a very widely used programming language nowadays because of the popularity of data science. But the language itself has been around for over 25 years and has been used very widely in the domain of statistical computing. For us as PL designers, R is a very interesting language to study because it has a very unique set of features. R is functional, imperative, and object-oriented, which is not a surprise. Most dynamically typed languages are. But R is also lazy, so it mixes laziness and side effects. R supports metaprogramming, so you can generate ASTs at runtime and evaluate them. R supports reflection. It allows functions to reflect upon the call stack, get information about all the callers in the call stack. It allows reflection on the bindings in the current scope or any of the parent scopes. And scopes in R are first-class objects called environments. So a function can just take its own scope, its environment, and return it as a first-class object. And the bindings in that environment can be accessed like the environment is a hash table. This talk is specifically going to focus on laziness and its interaction with other features of the language. So let's define laziness first. In the words of Paul Hudok, we call an implementation of normal order reduction in which recomputation is avoided, lazy evaluation, or call by name. That is, arguments in function calls are evaluated at most once. Let's try to understand the model through this example. Here we have a function f which takes two arguments x and y, and the body of the function uses only the argument x, it does not use y. Then f is called with two arguments, print a and print b. And when we evaluate this call, we only see a being printed on the console. And the reason is that in the body of the function, only x is used, and x is bound to print a. Y is never used, and the language is lazy, so print b never gets evaluated. The other thing to notice is that a is printed only once, even though x is used twice. That's because arguments in function calls are evaluated at most once. So when x is used the first time, print a is evaluated, and a is printed on the screen, and subsequent uses of x use the result of evaluating print the first time, so they don't recompute print a. Let's try to understand how this model is implemented internally. When a function is called in R, the formal parameters are bound to a data structure called a promise. The promise contains the unevaluated argument AST and the environment in which this AST is to be evaluated. When the formal parameter is used in the body of the function, the promise is forced. Forcing a promise means the expression is evaluated in the environment and the result is returned and cached inside the promise. Because of this caching, subsequent uses of the formal parameter return the value, the cached value from the promise instead of recomputing the expression. So arguments are evaluated at most once. In our paper, I described the design and implementation of the laziness in R in terms of a small step operational semantics. What I'm going to describe here are the key takeaways about the design of laziness. Our key takeaway is that R is rather strict for a lazy language. And that is because only argument evaluation is did. That is, when a function is called, only the arguments are wrapped inside these promises and no other expressions by default are wrapped in promises. So return values from functions, for instance, are evaluated eagerly. Even in assignments, the expression that is being assigned to a variable, that expression itself is evaluated eagerly. And apart from that, R does not have any lazy data structures by default. We have been using R in our lab for a while, plus we have anecdotal evidence that many users of R did not realize that R was a lazy language. And we hypothesized that perhaps R could be made strict by default. Right now it's lazy by default, but we could make it strict by default. And laziness could be an option for the users. A user could explicitly opt into using laziness by annotating the arguments to a function. So now let's think about how we can validate this hypothesis. We could modify the R source code, the R implementation, so that when a function is called, instead of creating promises, we just evaluate the arguments at the time of call. But the problem is that if we switch R this way into an eager evaluation mode, then the built-in functions will break. There are conditionals and exception handling mechanism which assume that the language is lazy. We could also manually go through the entire R source code and figure out what are the key places in the source code where functions rely upon laziness. But the problem is that this is manual work. It's very work intensive, and it's also very error prone and not scalable. There is millions of lines of R code out there, and we cannot really do this work manually. We also dropped the idea of doing static analysis to validate the hypothesis because R uses reflection pervasively, which makes it really hard to do a reasonable job. Since none of these approaches will work, we settled on a dynamic analysis to study how promises are used. And we augmented our study with manual code inspection to gather qualitative insights. So now I'm going to describe the methodology, which is basically the dynamic analysis infrastructure we developed for analyzing our code. And subsequently, I will talk about the result of that analysis. The first step we did was create a corpus. Our corpus contains 16,000 R packages. And from these R packages, we extracted 232,000 runnable R programs. The packages were downloaded from two package repositories, CRAN and Bioconductor. These are curated repositories. They are not a dumping ground for possibly broken code, as is the case for code on GitHub. For an R package to be accepted to one of these repositories, it must be equipped with runnable code that can be used for testing. Traditionally, packages come with three sources: examples, tests, and vignettes. Vignettes are long-form programs which demonstrate how a package can be used to solve a specific problem. What's important to note here is that these three sources of code, they are written by package authors. They are not written by end users. So we don't have end user code in this study. And the reason is we believe that end user code is not defining functions and hence is less likely to leverage laziness than a package. Because package programmers are the ones writing functions, they are more likely to understand R semantics and hence are more likely to leverage laziness. An important limitation of our approach is the fact that the data which I'm going to present later on, it depends upon dynamic analysis. So we may underestimate the use of laziness because we will only see certain code paths. We won't see all the code paths. Previous work suggests that on an average, 60% of the R code is covered by these three sources. So now that we have our corpus, the next step is to trace all of it. That is, we run the programs against a tracer and get some data about the use of laziness. In this step, we generate a file per analysis question for each program we trace. So here are two lines of R code. In the first line, we create a 2x2 matrix. And in the second line, we check if the matrix is symmetric. Now, checking if a matrix is symmetric is a simple operation. And when we trace this program, we generate 278 promises, just these two lines of code. Now in our corpus, we have 232,000 programs. They correspond to 25.6 million lines of code. So how many promises do you think this will generate when we trace it? It's a rather large number, 271 billion. Scale was a major challenge in this project. We faced difficulties both due to execution time and data size. In the 232,000 programs that we traced, we observed 1.7 trillion expression evaluations, which generated 11.5 trillion events. There were 831 billion function calls to 698,000 R functions. To investigate the use of laziness, we had to keep track of each of these promises. We had to track the function that created these promises, when and where they were forced, their interaction with metaprogramming and reflection facilities of the language, and numerous other details. So now I'm going to describe the infrastructure we developed for addressing this challenge. The first part of our infrastructure is Ardent Trace, which is basically an instrumented R virtual machine based upon the GNU R interpreter. Its goal is to produce program execution traces. These traces contain events that we need to answer our research questions. You can see some of these events on the right. We have events for function entry, function exit, promise force entry, promise force exit, various sorts of variable assignment definition, and other variable related events, GC events. And these events are obtained from probes that are inserted inside the R interpreter code. Now, on the face of it, this is not a difficult task. We only ended up adding less than 2,000 lines of C code. But this was very problematic, and we succeeded by a lengthy trial and error process. The challenge is in identifying where to insert these probes inside the interpreter, because the C code of the interpreter is over 500,000 lines of code, and it has been written for over 25 years by numerous developers. And over a period of time, it has grown in complexity with an eclectic mix of features. So just to give you an idea, the code to manage environments and variable bindings in R is over 3,000 lines of code, and it has 131 functions. There are two different environment representations, so there are identical code fragments which work on those two representations, which means that whenever we add a hook, we have to add the hooks in both the places. And this complicates our tasks. The second part of this infrastructure is the actual tracing logic. This is the part which intercepts the events generated by ardent trace and collects information about the use of laziness. This is an R package containing 73 lines of R code, which calls into a bigger C++ code base. It is loaded in the instrumented R virtual machine, and during program execution, it maintains objects that model various aspects of the program, such as functions, calls, promises, tags, stack frames, etc. Now, to deal with 271 billion promises, we took certain design decisions that allowed this tracer to scale. Firstly, we avoid copying model objects as much as possible, because we are dealing with so many promises and trillion of events. If we start copying object at each event, we will not be able to scale. To reduce tracing footprint, we modified the R garbage collector so that these model objects that we create, we deallocate them when the corresponding R object is deallocated. These model objects are linked together. For instance, for a given function, we know all the promises created by that function, so that when an event triggers a cascade of change, we can do it in constant time. And because of this linking, these model object lists can be circular, which means that we have to perform manual reference counting. Now, once we develop this infrastructure and we ran all of this on the 232,000 programs, we generated 5.1 terabytes of data. So this created another challenge. How do we store so much data, and how do we analyze so much data? For this, we developed our own data storage format, which relies upon Facebook's Z standard library. This library allows streaming data compression, and this works out quite well for us because the event stream generated by the R programs has a lot of redundancy. In this particular instance, we observed that there was a space savings of 10x with our format. And because the size of the data is reduced, and plus our own custom format also had a schema, we observed a speed up of 12x in storing and reading this data from the disk. So the raw data, which was 5.1 terabytes, was then subsequently brought down to 1.5 gigabytes for the final analysis of the use of laziness. This is an impressive amount of reduction. And for this, we had to develop a custom MapReduce style data analysis pipeline, which we executed on two large servers with 72 cores and 256 GB RAM each for over 2 weeks. So I'm going to describe now the different steps of this analysis pipeline. The first step was the reduce step, which is essentially applying an R function to the tables generated by the tracer. We use a tool called GNU Parallel to parallelize this across all the cores on the server. And this was the most expensive step. And this achieved an impressive reduction in the data size from 5.1 terabytes to 76 GB. The next step is the combine step, where we combine information for all programs into a single data table per analysis question per machine. So now we have two data sources which are stored on two servers. We copy them onto one server and merge them in the merge step. So now we have only one data source. Then in the summarize step, we apply some more analysis on the single data source to generate all the information, all the final results about the use of laziness in R. And finally, we also have an R Markdown report in which we summarize all our findings, including graphs and tables, so that we can look at the results. This entire pipeline is completely automated. I can run it on a new set of programs right now and update the paper to reflect the new data and figures. Developing this infrastructure was really hard, and the problem was we had to learn the many quirks and oddities of R while we were trying to develop all of this. So it was really, really hard for us to achieve stability in the design. It took us over 2 years to design this entire thing. And even this pipeline is simplified. There are lots of implementation details for capturing and reporting errors, which I'm eliding for the sake of time. All this infrastructure is reusable, and we are also using it now for addressing other questions about R. So now that we understand the methodology, I'm going to now discuss how R uses laziness. So the first thing we looked at was what kind of objects were being allocated by our corpus. We observed that promises were the most frequently allocated objects, as shown in this graph. Apart from promises, there are vectors of various kinds. R does not have scalar values, it only has vectors. So there are vectors of strings called character, vectors of booleans called logical, vectors of integers, vectors of doubles. There are also a huge amount of environment objects. They are the third most allocated objects in the corpus. This is because every time a function call happens, a corresponding environment object is created to store the bindings. Another interesting data point is that 87% promises are forced. Now, laziness is typically added because the hope is that by delaying argument evaluation, we can completely avoid evaluating that argument if it's not needed. But this number seems to suggest that most arguments are anyways being evaluated. So this leads us to investigate if programmers are taking advantage of laziness. If they are taking advantage of laziness, then we cannot get rid of it. On the top right, you see a function f, which takes two arguments, sometimes and always. The arguments are so named because the always argument is evaluated across all the code paths, and the sometimes argument is only evaluated across one code path. Now, if programmers are taking advantage of laziness, we could expect that they will pass complex arguments to sometimes positions, because then they would save on the evaluation time when the argument's value is not needed. With this in mind, we looked at the evaluation time of all the complex arguments in our corpus, and we made this density plot. In this density plot, the x-axis is the time it takes for the argument to evaluate, and on the y-axis, we have the two argument categories, sometimes and always. The width of the graph at any point tells us the proportion of the arguments of that type which take that much time to evaluate. Now, if programmers are taking advantage of lazy evaluation, we would expect that sometimes argument graph will have a bulge significantly towards the right. On the contrary, we observe that there is a very small difference in the shape of the two graphs. In fact, the sometimes arguments take a median time of 2 milliseconds to execute, and the always arguments take a median time of 3 milliseconds to execute. This might suggest that programmers are not taking advantage of lazy evaluation, but we stop short of making that conclusion. This is because we are dealing with a huge number of promises. There are 3 million sometimes promises coming from 16,000 R packages. So maybe there are a few hundred packages where programmers are taking advantage of lazy evaluation, where they are passing complex arguments to sometimes positions, but those promises get buried in all this noise, and it's hard to separate them. So we start looking at data from a different angle. We start addressing the cases where we already know from experience that programmers are taking advantage of laziness. First case that comes to mind is metaprogramming. Metaprogramming support of R is shown in this picture. In R, there is a function called substitute, and the substitute function reflectively accesses the argument AST from the promise to create ASTs in R. So you can pass a complex expression to substitute, it will walk over it and replace each formal parameter in this AST with the unevaluated argument AST for that formal parameter. We observe that 2 billion promises are metaprogrammed using substitute. That is a small number. It's only 0.7% of the 271 billion promises that we observe, but it's quite widespread. There are approximately 2,000 R packages which are doing metaprogramming using substitute. This got us curious about the use of metaprogramming in R. Why are so many people doing metaprogramming, and what are they using it for? The most common use of metaprogramming in R is non-standard evaluation. I'm going to explain this with the definition of the pipe function as it's implemented in R. The pipe operator percentage greater than percentage works as follows. It takes a thing on the left, evaluates it, and passes it as an argument to the function on the right. So df pipe mean is equivalent to applying the mean function on the df argument. And the way pipe operator is implemented in R is that it is a function of two arguments, LHS and RHS. And then it applies substitute on LHS and RHS to get the unevaluated argument ASTs. And then it uses eval on the LHS and RHS in the parent frame. I've elided some implementation details here for the sake of clarity. The parent frame function reflectively accesses the parent environment. And in that parent environment, eval is being called on LHS and RHS. Now, what's interesting about this definition is that it brings together a couple of interesting features of R. There is metaprogramming, which builds upon laziness. Then there is parent.frame, which reflectively accesses the parent caller's environment. The environment itself is returned as a first-class object. And then there is dynamic evaluation of the AST in that environment. This pattern of usage of features in R is called non-standard evaluation. And it's quite pervasive in some of the most popular packages of R because it's used for creating domain-specific languages. And there are domain-specific languages in R for analysis of tabular data, for plotting, and even object-oriented systems. All of them are built using this particular feature. The other use of metaprogramming in R is syntactic convenience. So R defines this : operator, which is used to specify the fully qualified name of an object. So we can write base : filter to access the filter name from the base namespace. And the definition of this operator is as follows: takes two arguments, package and the name. Then the package and the name symbol are extracted using the substitute function and converted into a string using as.character. And then the get function is reflectively used to access that variable binding from that namespace. So these were the two most common uses of metaprogramming in our code base. After that, we got curious about the use of lazy data structures. Lazy data structures are the most widely touted benefit of laziness, and R does not have any lazy data structures to begin with. But it turns out it's very easy to create them using environments. So here in the top right, I have created a lazy list with just 4 lines of R code. And the primary workhorse here is the cons function. The cons function implements the cons cell of the lazy list. It takes 2 arguments, h and t, which correspond to the head and tail of the list, and it just returns the result of calling the environment function. The environment function returns the environment of the cons call, and this environment has bindings to has the h and t bindings. And because the language is lazy, h and t are bound to the unevaluated head and tail of the list. So there are 2 interesting aspects to this definition. The first, that the function can return its own environment as a first-class object. And second, the promises bound to h and t are bound in the environment and they can outlive the frame of the cons call that created them. So these promises escape. Now our goal is to identify the creation of lazy data structures in the millions of lines of R code that we have. So essentially, we are interested in identifying this particular pattern of functions, that is, functions which return environments and whose arguments escape. This graph demonstrates quantitatively the number of such functions. So here on the x-axis, we have the proportion of such functions, and on the y-axis, we have the return type of those functions. We are interested in functions which return environments, which is shown in the red box. And more importantly, we are interested in functions whose arguments escape, which is shown by the red bar. So we manually analyzed all the functions in this category, and we found that there is only one function in a package called rstackdq, which implements a lazy list. And no one else uses this package. So for over a period of 25 years, there have been more than 16,000 packages written in R, and no one is using it to create a lazy data structure, or at least no one is relying upon that lazy data structure implementation. The third use of laziness we found in the corpus is delaying expensive computation using delayed assign. The delayed assign function can be thought of as the delay function of scheme. It takes 3 arguments, the variable, expression, and environment, and it binds the variable to a promise containing the unevaluated expression. The binding itself is created in the environment, which is passed to the delayed assign function. There are 82 million calls to delayed assign spread across 36 R packages. So we have 16,000 packages in our corpus, out of which only 36 packages are using delayed assign. The important point to note here is that this particular use of laziness is explicit. Delayed assign is being called explicitly. It does not require the language to be implicitly lazy. Just like scheme is not lazy, but it still supports the delay and force functions. The delayed assign function is mostly used to delay expensive computation. There are three calls to delayed assign from a package called Azure ML. In this package, the developer is trying to create a workspace which contains three variables: experiments, datasets, and services. And the idea is that when a user uses any of these variables of the workspace, then it fetches the corresponding data from the server using the get experiments, get datasets, or services function. And the package developer would like to delay the calling of these functions until they are actually needed. This kind of a pattern was quite common across the 36R packages, which were using delayed assign. And one particular package was also creating a disk-based key value store using delayed assign. So what we have seen so far is that implicit use of laziness in R is only there for metaprogramming. No one is creating lazy data structures. And there is a little bit of use of explicit laziness using delayed assign. However, this combination of laziness, side effects, and first-class environments creates interesting challenges for users and developers. Here is an example extracted from the RBug tracker, which was reported by a user who found this particular example very confusing. Here a function f is created, taking a single argument x, and returns an inner function which captures x. Then a variable y is created, it's assigned the value 2. Function f is called with the argument y, and the result is assigned to g. At this point, g is bound to the inner function of f. Then we assign the value 4 to y and call g. Now what will happen when we call g? The inner function of f will be executed. This will cause a lookup of an evaluation of the promise bound to x. That promise contains the symbol y. Y will be looked up and its value will be 4. So 4 will be returned. Now for the user, this behavior was confusing because they expected the call to g to return 2. And the reason is that g was created at a point when y's value was 2. So they expected that call g should return 2. What's even more confusing here is that if we further modify the value of y to say 6 and call g again, we again get the value 4. This is because the first time g is called, the promise is forced and its value 4 is cached. So subsequent calls to g will look up the cached value inside the promise, which is always 4. So regardless of what the value of y is in subsequent calls to g, it will always return 4. And you can imagine such a behavior could be very confusing to users who do not understand the semantics of laziness and its interaction with side effects. In fact, the problem is so severe that the R developers were forced to add a function called force and call. This function forces the arguments of a function in a predefined left to right order and then apply that function to the arguments. There are 1.3 billion calls to force and call in our corpus, and all of them originate from higher order functions. So all the higher order functions in our map, filter, reduce, they all internally use force and call. And apart from that, in normal functions also, we observe that developers explicitly use the force function to predictably force the arguments to the function in a left to right order. Some programmers create their own variants of force functions, such as the force solve function in this example on the bottom right. This is taken from a package called Viridis. Here the function takes 4 arguments A, B, E, D, and the package author calls force all on A, B, E, D to make sure they are evaluated in a left to right order before they are captured by the inner function. So what this suggests is that the semantics of laziness and side effects are confusing for the users and package authors, and they would prefer a predictable argument evaluation order. Now we know that promises are plentiful, and most of them are anyways forced, and they are a source of headaches for users and implementers. The question is, can we deprecate laziness from R? So let's think about what kind of promises we can easily remove. On the top right, we see a call to H in the first line. There are 2 calls to H. In the first call, we pass a string. In the second call, we pass a number. In these cases, removing laziness is not a problem. We can remove promises because those promises only package values, which are non-computations. Values evaluate to themselves. But in the second call to H, the situation is tricky. It's a call to the function G, and this can be potentially side affecting. So we cannot just blindly remove laziness in this case. To understand this better, here is an example of a function f which takes two arguments a and b. If a is true, it returns b, otherwise it returns 2. And now we call this function f with two arguments, false and x assigned 23. Now because a is false, the assignment of 23 to x will not happen. But imagine we turn this language from lazy to strict. In that case, the assignment of x to 23 will happen even before the call to function f happens, and because of this, the code will break. So because of side effects, it's not possible to just remove laziness like that. So we looked at the type of our expressions inside promises in our corpus, and we found that only 17.3% promises contain a function call. Rest of them contain values. And apart from that, only 0.006% of these promises actually perform any observable side effect. So what this suggests is that in most cases, it's possible to remove laziness. But this itself is not enough. So here is a function f which takes three arguments xa and b. And if x is true, we evaluate a, then b. And if x is false, then b is evaluated and then a. Now this function is called with it's called two times. The first time it's called with x true, and the second time it's called with x false. And the remaining two arguments are the same. Now depending upon whether x is true or false, the final assignment to e will be different. So because of laziness, the two side effects are interfering, and the two calls will result in different values of e. What's interesting here is that this function has to be lazy. There is no way to convert it into a strict function, because if we convert it into a strict function, we will have to choose one particular order of evaluation of arguments, which will break at least one of the calls. So this brings us to evaluation orders of function arguments. In our corpus, we observe that 94% functions have a single evaluation order. So they don't exhibit the kind of problem shown by the function f here. And the graph shows the functions with remaining higher evaluation orders. We observe that roughly 4.7% functions have two evaluation orders, and a progressively decreasing number of functions have higher evaluation orders. Higher evaluation orders typically happen when a function takes multiple arguments. In R, it's common for functions to take 15 to 20 arguments or even more. And typically only some combination of those arguments are used across one code path for parameterizing a statistical function. So this data is encouraging. It suggests that 94% functions have a single evaluation order, so that makes it easy if we want to remove laziness. But this condition itself is not sufficient. We also care that the function should evaluate all of its arguments. Functions that evaluate all of their arguments in a single preordained order are strict functions. There are 84% strict functions in our corpus. This means for these functions, we can remove laziness easily. Instead of creating promises, we can evaluate all of their arguments when they are called. We also looked at the spread of these strict functions across packages. And in this graph, we see that more than 50% of packages only have strict functions. And 17% packages are less than 75% strict. So what this suggests is that most of the R code base out there is written in such a way that it's very easy to remove laziness from it. So now the question is, how do we remove laziness? The approach we are exploring is adding a new language feature we call annotations. And the idea is that parameters that require laziness can be annotated with the @lazy annotation. And the implementation will create promises only for these arguments. For the remaining arguments, they are evaluated eagerly. So the question is, how do we add these annotations? We could rely on the results of our dynamic analysis, but dynamic analysis can miss certain code paths which are not covered by the inputs. So we could also perform a static analysis of function definitions and find arguments that are not executed across all code paths and annotate them as lazy. So consider this example on the top right. We have a function f which takes three arguments, x, y, and z. And this function adds x to the result of calling g on y and z. Now g always evaluates y, but it may not evaluate z. So just by looking at the body of f, we can conclude that f is strict in x. But if we want to find out whether y and z require a lazy annotation, we will have to jump to the definition of G and analyze the body of G. For dynamic languages like R, doing this kind of control flow analysis can be challenging. So how often do we have to do it? For this, we concretize the notion by computing the evaluation depth of a promise. Evaluation depth of a promise is the number of call frames it takes for the promise to be evaluated. In the case of function f, x has a depth of 1 because it's evaluated immediately inside f. But y and z are forwarded to G, so they have a call depth of 2. And what this graph demonstrates is that most promises have a call depth of 1. 80% promises have a call depth of 1. So they are evaluated in the callee itself. So for the remaining arguments, we can either make the conservative choice of just saying they're always lazy, or we can do a control flow analysis and figure out precise signatures. So what about metaprogramming? Similar to laziness, to lazy annotations, we are thinking of adding in @meta annotation for metaprogramming. So here we have a function f, which calls substitute on its argument x. We can infer this dynamically or statically. And for these formal parameters, we can annotate them with the @meta annotation. And in this case, the implementation can bind the parameter to the unevaluated argument ast, which can be retrieved using the substitute call. This works 99.7% of the times. The remaining 0.3% of the times it works, but it is very brittle. So here you see a function f, which takes an argument x, and it calls g. And G reflectively performs substitute on X. G itself does not perform substitute on its own argument, but on the parent, on the argument of the parent. Now this setup is brittle because if we were to add meta annotation to X, the body of F itself does not use substitute, and the definition of G can evolve independent to the definition of F. So imagine that G could be in another package, and the next version of the package removes the call to substitute inside G, and the annotation will go stale. So this setup is very brittle, but fortunately this happens only 0.3% of the times. So perhaps we can live with it. And this is the current state of affairs in this project. We are modifying the R parser to support annotations and working on an algorithm to infer laziness signatures for functions. So with this, I come to the end of my talk. To conclude, laziness is mostly needed for metaprogramming and extensibility. Laziness, side effects, and environments are hard to analyze, and R does not have to be lazy by default. We are designing an annotation system for strict R, and our goal is to perform a non-intrusive migration of R code by automatically inferring these annotations. Thank you.
Thank you. Do you have questions? So you mentioned at some point that there is very limited static analysis for R. Is like, besides this work you've been doing, are people trying to build static analyzers of any kind?
Not to my knowledge. So some of my colleagues, they are developing a JIT compiler for R. So they have a static analysis framework, but it's on their own intermediate representation. And I am currently working on doing some static analysis on R source code.
Okay, I guess a related question is, I guess, what do R programmers care about? Like, what is their biggest worry?
So R programmers, in our opinion, would care about efficiency. And the problem is that the fact that the language is lazy makes it very hard to optimize. So R is one of the slowest dynamically typed languages, and it's much slower than Python. And in our experience, when we were designing this JIT compiler for R, we observed that laziness is one of the major blockers. And the idea is if we can remove laziness and show to the users of R that by adding these annotations, by making your code strict by default, you can get a good performance boost, then perhaps they would be interested in having these annotations.
Other questions?
This is Tom. Is there a trivial migration where basically every parameter has an annotation that it's lazy?
Sorry, could you repeat that question?
So are you guaranteed that you can always migrate R code because there is a trivial inference, which is to start with every parameter having the annotation lazy?
Exactly, yes. So whenever we cannot decide, we can just make it lazy.
Okay.
I mean, the reason we think we'll be successful is because we have looked at hundreds of functions, did qualitative analysis, and we observed that in most cases, just by looking at the body of the function, we can figure out whether an argument is lazy or not. So if we just did something very simple, looked at the body of the function, most of the arguments would be stripped. So we will rarely have to add this lazy annotation.
Do you have any idea why they incorporated laziness when they started 25 years ago?
Non-standard evaluation. So their idea was they didn't like macro systems. They wanted language to be extensible. So they thought that if they can delay argument evaluation, then they can reflectively access the AST. So during that time, there was this thing popularized by Lisp programmers called an fexpr. So fexpr is like a normal function, except that this function takes AST arguments. So the design in R was somewhat influenced by fexprs.
And is there any use of infinite data structures?
We could not find anything. And there's a good reason why, because R was really designed as a shell over C and Fortran. I mean, most of the R functions eventually call into C and Fortran code for numerical computation. And these libraries expect the data structure to have a particular format, like values have to be stored in contiguous memory locations, right? So
yeah,
creating infinite data structures, like there is little use for it. We could not find anything there.
So nobody's done something like, well, I think like constructive reals. Do they use laziness?
No, absolutely nothing.
Nobody uses that.
No.
You're saying? I see.
Hi, this is Justin. I had thanks for the talk. I had also one question about have you thought about doing this kind of analysis for other languages? Like Haskell is another language that is well known for being lazy, but there's some debate about how much people use it and how much laziness is important. So do you think this kind of analysis might work for other languages?
I don't think so, because the design of Haskell is very different. So with R, the problem is that it's dynamic, side effects are unconstrained. In Haskell, there is this monadic approach for managing side effects, so it's more organized. It would be definitely interesting to independently do a study of use of laziness in Haskell and figure out how much of Haskell code actually requires laziness. But I don't think the analysis we are doing for R can be used as is for Haskell.
I see. Cool, thanks.
Yeah.
Okay. If there are no further questions, we can thank Aviral. And that's it for today.
Great. Thanks, Aviral.
Thank you.
Thanks for coming.
Thank you. My pleasure.